make sure I'm on camera. Okay, so let me introduce you. We're very honored today to have Professor Zhang, who's not only the vice chair of the machine learning department here, but he's also the director for the Center for Artificial Intelligence, which means he's my boss, because I'm from the CIAI as well. And then today he'll be giving his talk on causal representation learning advances and perspective. So please take it away, Kun.
Thank you very much, Zhang. Welcome to MBZUAI. So if you need anything, please let us know. We are local hosts. So thank you very much to the organizers and especially to Zhang, Phil, Silver, really, yeah. So welcome. Okay, so today I'm going to talk about the causal representation learning. I'm going to report some advances, and at the same time, I'm going to share some perspectives. So you can see that in this task, we care about not only causal of the learning the system, but also the causal property of the learner representations. Essentially, we would like the learner representation to be composable, right? And scalable, and at the same time, we would like to have an automatic approach with as few interventions as possible to learn those things from data. So here you can see, first of all, we really care about the causal representation or causality. If you want to do domain generalization or domain adaptation, you try to see how different scenarios are connected. And then because of connection, you can do transfer. And when we make decisions, clearly we have to give a reason, right? We have a reason. And when we make decisions, usually we want to change something, right? Clearly you care about the effect of interventions, and you want to see what part to change in order to make it effective. And when you make recommendations, the same thing will happen, right? You have to give a reason, at least you have to give the expected outcome. And similarly, when we are recommended, right, machines recommend something to us, we would like to see the results. Essentially, it's about explainability and actionability of the machine learning problem, of machine learning, of the outcome of machine learning systems. Furthermore, here you can see a very famous example to demonstrate a common problem in deep learning systems. We have essentially the adversarial vulnerability problem, right? It's dependent, but after you add some noise of a particular pattern, or if you change some pixel, all of a sudden machines say, oh, it's something different. Why? Why could it happen? How can we really avoid this problem? So we have some recent papers on it. Basically, mathematically you can show the following thing. As long as machines and human beings actually learn and make use of different sets of high-level representations of the features, then this is always the case, because you can always tune the input, raw input, so that either machines or human beings, right, will say something different. That means in order to make sure machines and human beings can really communicate with each other seamlessly, what can we do? We have to understand what kind of feature representation we learn and make use of. And we have to equip machines with the same ability, right? To learn features consistent with what we use. Then next question is, what kind of features do we use? Here, let me just say a few words about causality. From data, we know dependence. You can use the joint distribution, conditional distribution, or some other measures, right, to describe how they are related. But when we say causality, it's more informative. Here, X and Y may have the same dependent pattern, but the causal relation can be totally different, right? If X causes Y, as you can see from here, you cannot see it. So if X causes Y right here, you can see intervention on X will change Y, but in the two alternative models, even if they are correlated or dependent in the same way, intervention on X will not change Y. So clearly causality will be more informative, and we want to understand how. Now, next question is, why do we need causal representations, right? Let's try to give a more fundamental answer. Some people say, with the causal representations, we can really benefit some downstream tasks. Yeah, that's the case, right? We have a lot of evidence, but still we need to provide evidence. And sometimes we say, yes, we care about the why questions. So this provides a way to answer such questions. That's good, right? And furthermore, some people may say, actually, we are trying to recover the property of the true process. That might be the case, but the true process could be very complex. Here, I would like to give a further philosophical argument. So basically, this is the world of experience. I can stand here, right? So this is the world of experience. This is basically the world we can perceive. And right here, according to Kant, this is the Kant's metaphysics. So this is our world, and that's the world in itself. But we can never directly perceive anything of world in itself. We can only have we can only perceive this guy, this world, and whenever we see something here, we already applied some forms of experience. Basically, it's like a filter. So this filter system consists of concepts of space, time, causal order, and so on. So that means that whenever we try to analyze something, we already have the information of causality right there, and time information, space information, and so on, right? Given that, we would like the machines to have the same ability. The machines can automatically apply causal understanding, the concept of time, and so on to the data and discover consistent representations. Okay, so we care about the representations. And furthermore, how can we make it possible? We have only observational data. How can we really recover causal information from data? To answer this question, we have to address two issues. First, what kind of information in the data actually can reflect causal information? In other words, what kind of footprint can we find in data? Footprint of causality can we find in data? So I'll talk about that. The second question is, given the constraint or given the property of the data, can we recover the underlying causal model or structure uniquely? This is about identifiability. It's the identifiability of the underlying causal structure from data. So the answer to the first question is essentially known as the modularity property of a causal system. So here we are talking about composable representation, the composable learning process. This is the modular representation. They are somehow related. By modularity, I mean the following thing. We have a causal system right here. Even if all those variables, including rain, wet ground, slippery, are dependent, actually we have separate, irrelevant modules. Those modules are not related to each other. One module generates rain. The second module generates wet ground from rain. The third one generates slippery from wet ground, and so on. So those modules do not share parameters. They are completely irrelevant. We can change one without changing any other. If they change independently, right? So this is modularity property. Essentially, this is the most fundamental property of a causal system. We view this world in a very simple way because of causality, right? We can automatically decompose very complex systems into a lot of simpler modules, and then we can put different modules together to establish some big system. Okay, this property, modularity property, immediately gives rise to three properties that we can see in the data. First one is the conditional independent relations in the variables. The second one is the independent noise condition. Basically, the noise would be independent from the cause if there are no latent confounder. The last one is the minimal and independent changing property. So basically, if you see changes in non-stationary environments or heterogeneous environment, then the changes would be minimal and independent, right? So this is because right here, those modules are not related. If you have change here with the wrong representation, you are going to suffer more changes, and the changes will be dependent. Okay. The second thing is how to establish identifiability. So all those approaches or developments I'm going to report have identifiability guarantees. By that, I mean the following thing. Under the appropriate assumptions, you can show that the learned representation, like causal structure, latent variable, and their relations, will be consistent with the underlying truth that you assumed, right? Okay, now let's consider the problem, the three axes of the problem. First, what kind of data do we have? Do we have ID data as input? Or do we have heterogeneous or non-stationary data or temporal data as input? So this is the first dimension. The second one is whether we can benefit from some parametric constraints, like linearity constraints, right? In some cases, if you know the system is almost linear, then the problem can be simpler. The last one is whether we allow latent confounders. Of course, in this world, we have latent confounder almost everywhere, right? So practical methods usually can deal with the latent confounders. Now let's see how we can do. This is the basic summary of the recent advances in the field. So you can see for each setting, right? Basically, each combination of the three axes. Then on the right, you can see what we can get. So in the ID case, basically the problem is very hard. We have only a single distribution. So usually we can end up with some equivalence class. And if you are willing to make some further assumptions about the causal influence, then in some situations you can recover the underlying truth uniquely. But basically, in a non-ID situation, the problem will be simpler. Okay, you will see why. So here, let me start with an example. So this is a data set collected by my collaborator, Marlin Novak. So in archaeology, they really want to see why people in different areas look different, right? They collected 250 skeletons. They try to see the reasons of the difference. So the features including sex, cranial size, diet, location, climate, and so on. So in this case, clearly we cannot really do intervention. We have to analyze the data, and the relation can be very, very nonlinear. We have no idea. Some features could be very high dimensional, like cranial shape differentiation, right? It's 255 dimensional. Here we just apply the PC algorithm developed by Peter Spertit and Clark Glimmer, PC, combined with the kernel-based conditional test. Now we can say we only make use of a conditional independent relation in the data, but you can get something very informative, right? From the data set, we know, oh, gel distance, it causes the climate causes cranial size, you can see gender causes the cranial size, and so on. So by only in conditional independence, you can already find something in the data. Of course, here we assume there are no latent compounder, so you want to go further. And furthermore, with the conditional independence, sometimes we cannot find the direction. If you have only two variables, right, you can only say whether they are independent or dependent. You cannot find the direction. But if you make some rather mild assumptions about the causal mechanism, all of a sudden, cause and effect are not symmetric anymore. You can really figure out which one is the cause and which one is the effect. In the linear non-Gaussian case, as you can see from here, from cause to the effect, right, you can find the independent error, but from effect Y to cause, you can never find an independent error, although the residual is always uncorrelated from the predictor by construction of linear regression. So you can see asymmetry. In the wrong direction, you cannot find an independent residual. The same thing happens even if you have very flexible model, post-nonlinear model, or kind of a special case, additive knot model. So here, this is a measure, is a way to measure sensor measurement distortion. It's very important, this function in practice, because very often times we have a lot of distortions. But basically, we can find the causality from data if you assume there are no latent compounder. Okay, so that's the first part. We developed the so-called causal learning package. I talked to you about it. So this package contains implementations of almost all those state-of-the-art causal discovery methods that are proven to be kind of somehow reliable. And in most of them, we don't really deal with the latent compounders. So that's a second part of the talk. And we try to use a composable implementations. Essentially, as you can see from here, we analyze all those methods. We try to see which modules are shared and which, right? And then we have a hierarchical way to organize all those modules. So in this way, you can see users can easily make use of some functions and implement their method. And basically, the package is easily extendable and refinable. So this is how we implement the package. I would like to get some suggestions from you because you guys are professional in this particular field. Now, you can see we try to analyze the relations, right, among different methods, and we find the algorithms and the modules and so on. And finally, we have a very nice way to organize all those modules. Okay, now let's go to a kind of more difficult situation. How can we recover the latent compounders and their relations? So here, this is the motivating example. We have answer scores in psychometric studies, right? We have questionnaires, then we can collect answer scores. From the answer score, what can you get? Or what would you like to get? We want to get the underlying mental conditions, right? The answer scores are not directly causally related, although they are dependent. It's just like image pixels. Nearby pixels are related, but they are not directly causally related. We cannot say this pixel causes another pixel, right? So we want to find the high-level latent variables and their relations. Okay, so in the last years, we developed a couple of sets of methods. Here, let me just briefly report the result on one data set, the teacher burnout data set. Here, they measured 28 variables, and they had 500 data points. So this is a model given by experts. So they don't rely on data. They just make use of their domain knowledge to produce this hypothesized model regarding how those variables are related. Here, those are kind of latent variables, and you can see latent variables are related. And with our kind of recent method, we got almost identical results. So it's cool. Basically, verify two things. First of all, the domain experts are very good because they didn't look at data, but they produced something that can be verified by data. At the same time, computational method could be very useful because you can really recover something about the domain knowledge. Okay, now we can go further. So in recent works, we try to recover the deep hierarchical structure by analyzing the measured variables. So here you can see with only xi variables as the input, you can recover the whole hierarchical structure, including latent variables and their relations. Okay. Later you can see how you want to kind of make it even better. And this is the ID case. If you go beyond the ID case, all of a sudden it's much simpler. Let me just give you some examples. So this is our result on learning underlying representation from time series data, say video data. Basically, let me just give two results on very simple data sets. So this is the KT mask video. With this video basic pixels as the input, we immediately recover the 3 latent processes. Turn out that they are independent. So the first one is the movement in one direction, and the second one is the movement in the orthogonal direction, and the last one is the size of the mask. In the second data set, which is known as the mask screen video, you can see here we have 5 balls in different colors, and between some pairs of balls, they are hidden springs. So with this video as input, we recover 10 latent processes. They are just XY coordinates of the 5 balls, and we also recover the location of the spring. As you can see how they are related. By making use of some causal principles, it is completely possible to learn the underlying representations, underlying concepts, and their relations in a completely unsupervised learning manner. Okay, so do I still have time? Okay, I'll finish. Oh, 5 minutes. Okay, I'll finish the screen. Thank you. So now let's go further. So I will talk about temporal data, like ID data, and temporal data like time series. Now, in many cases, we have non-stationary data or heterogeneous data. We have multiple distribution. Actually, from a causal perspective, this kind of data set is so useful. Why? Because without changing anything, we can forget about the causality. We talk about causality because we want to change it. We want to understand why and how they change. We want to apply changes, right? So in other words, causal modeling and the distribution shift are heavily coupled. If you know causal model, you know how the distribution may change. They change, right? Different modules can change. They must change independently, and so on. In the other direction, if you can see distribution shift in the data, then you can easily verify whether a particular hypothesis regarding causality holds true or not, right? You can see whether, if this model is true, here I can see some extra dependence, then you know, it's not plausible, right? So we did some work regarding how to recover causality from non-stationary or heterogeneous data. So I would say this set of methods would be more reliable in practice. Why? Because actually you rely on more information. You have more distributions, so it's more informative. Let me just briefly say something about this method, which is just causal discovery from non-stationary or heterogeneous data, CD0. First of all, from data, we can figure out for which variables the causal mechanisms change over time or across different domains. So you can say, for V1, the generating process changes. And the second, we can find a true causal skeleton. And then by making use of the independent chaining principle, we can find the directions of causal influences. Okay. And lastly, we can also find a low-dimensional representation of the change in the causal mechanism. Why? Because the causal mechanism can be represented by the conditional distribution of the target variable given the parents. Now you just want to find a low-dimensional representation of the change of this kind of complex conditional distribution thing. We use the kernel method with embeddings. Okay, so good. Now we can do something from non-stationary data. Furthermore, in the previous one, we assumed that we only allow a specific type of confounder, latent confounders. And in this recent work, basically the message is very clear. We have non-stationary data. And then if you assume that the difference in the distribution is caused by, say, the change in very few underlying components. And if you assume that the underlying components are independent, then you can immediately achieve the following thing. First of all, for the underlying component with change in distribution, you can just recover the component without any problem. So we can recover this component or this concept up to some invertible function for each of them. So that's good. So we can recover the components. And for the invariant things, right, which have the same distribution across different distributions, different domains, then we can only recover them up to the subspace. That's completely sensible, because if there are no change right here, what can I do? I can only recover, say, function or subspace of all those concepts. In other words, whenever something changes, we can recover it. If it's always the same, then basically it's a part of background. We cannot recover it, right? So that's the message. Now, this is basically the second to last one. You just saw that causal representation learning benefits from non-stationarity and heterogeneity. That means that if you have more distributions, then it's easier for you to learn causal representations. And the current approach basically just puts all data together and then try to learn something from the whole big data set. That's not really what we do, right? We learn those things sequentially, right? So here we have this representation, but we can just generate new concepts. We learn sequentially, we can generate new concepts. We can refine our previous understanding, and we can allow a huge number of concepts on our mind. So given that, we would like to have the kind of CIAI property of the learning process and the learning outcome, the learning output. Basically, the learning concept should be composable and extendable. And the learning procedure should be scalable with respect to the size of the data, the dimensionality, and the model size. And we should have an automatic procedure to do so. So this is the basic. We are right now looking at this problem. We try to use the continual learning and some other way to deal with the problem. Okay, to summarize, we care about causality. A lot of problems in machine learning actually are related to causality. In the second order, with appropriate representation, we can really allow machines to do something we can trust. Essentially, the way to achieve explainable and trustworthy AI. And it is possible to learn causal representations or pseudo-causal representation. By that, I mean the following thing. In some cases, we don't have those assumptions, but you can still use the representations as a way to achieve, say, some very good properties, although they may not be the causal model. And finally, you can see that the design of the kind of tensor procedure for learning the causal world really needs a lot of efforts. So I'm looking forward to your contribution in this line of research. Thank you very much.